All right, David. Dave Blewett from APL is first up with Lunar Vertex. Stage is all yours, David.
Okay, good. Thanks. Fun to be here to talk about a magnetic anomaly. Okay, I guess I have to click to advance. Right. So, lunar magnetic anomalies are really interesting from a number of perspectives. The moon lacks a global magnetic field, but there are local patches of magnetized crust. The origin of these magnetic anomalies is unknown, and there are several hypotheses for their formation. These fields modify the moon's interaction with the solar wind from what it would be if the moon was just a dielectric sphere. Observations from a number of spacecraft have shown that standoff regions or mini magnetospheres exist over the stronger anomalies. Modeling has also provided insight. There's an example shown there on the right. But the flux and energy of the ions and electrons that actually reach the surface are unknown. Then there's the matter of the lunar swirls. Most magnetic anomalies are co-located with unusual albedo features called lunar swirls. The type example is Reiner Gamma there in Oceanus Procellarum. The origin of the swirls is unknown, and there are several hypotheses for where they came from. So I think the magnetic anomalies really represent superb natural laboratories. They're a place where we can go to examine sets of key questions in several different areas of planetary science. I see these as really compelling problems that bring together what Don Wilhelms in his book To a Rocky Moon called sky science, right? Particles and fields. They bring that together with geoscience. And one in particular, when it comes to space weathering, it's likely that the surface within a magnetic anomaly experiences an atypical space weathering environment. It's thought that the two prime agents of space weathering are solar wind exposure and micrometeoroid bombardment, but the shielding effect of the magnetic field should attenuate the solar wind to some degree, but it won't affect the micrometeoroids. So we've really got a great control experiment on understanding these two key variables. So, among the unique opportunities that are presented here, we can look at problems in planetary science, including geophysics. What is the nature and origin of the magnetized crust? Does it involve an ancient dynamo and remnant magnetism recorded in intrusive or extrusive rocks? Or could these magnetic anomalies be related to field amplification effects associated with plasmas, associated with basin forming or comet impacts? There's the space plasma physics angle, the formation of the mini magnetospheres, the flux of these species that make it down to the surface, and how do these all change with time of day? And of course, the geology and surface processes. I mentioned the space weathering, the solar wind versus the micrometeoroids, which may be involved in the origin of the swirls, but there are other hypotheses, including unusual motions of levitated dust or interactions with dust and gas in the coma of a comet. And also there's the potential for unsampled rock types with unusually high metallic iron contents, depending on what we determine the actual inherent magnetization of the magnetic source to be. So my colleagues and I have been promoting a magnetic anomaly as a mission target for quite a number of years. Fortunately, apparently NASA was persuaded because last year the target for the PRISM-1A mission delivery was announced to be Reiner Gamma. So at APL, we responded to that announcement by writing a proposal, the cover of which is shown there. And the goals of our mission were to investigate the origin of magnetic anomalies, determine the structure of the mini magnetosphere over Reiner Gamma, the Reiner Gamma magnetic anomaly, address the origin of swirls, and then in the process of doing those first three things, you kind of end up doing the last two. One of which is, again, evaluating the relative importance of the two perceived chief agents of space weathering. And we can also provide some data related to certain strategic knowledge gaps, SKGs, for human exploration. In order to accomplish those science goals, we have a set of instruments on the lander. There are three on the lander. The first is an array of fixed cameras that provide a 360-degree panorama view of the landing site to help understand the context and geology. And those data will also be used for photometric modeling. There's a magnetometer. We're going to a magnetic anomaly after all. So we have a primary ring core flux gate that's on a mast. And with it, there are 4 inboard magnetometers that serve to sense the lander field. Now, importantly, the magnetometer will make measurements during descent as well as afterwards on the surface. That descent profile of the magnetic field strength and direction is really key for helping to constrain the nature of the magnetic source. And we have a solar wind spectrometer to measure ions and electrons in the plasma energy range that are incident on the surface of the moon. We also have a small rover that will deploy from the lander. It will carry 2 instruments. It will have another magnetometer that is a copy of part of the lander mag. This will allow us to determine the spatial variability of the magnetic field. And we have a close-up imager or multispectral microscope that will provide data on the composition and texture of the regolith beneath the rover during science stops. So, for this, it's really important to get away from the area messed up by the lander rocket exhaust so that we can examine pristine areas away from the lander. Although it will be very interesting to examine and compare the lander disturbed regions with areas farther away, kind of at the microscopic level, for comparison with the sorts of changes that are observed around landing sites that are observed from orbit. Our landing site will be somewhere near the edge of the large central bright swirl region at Reiner Gamma. This will give the rover the chance to make a traverse toward, into, and hopefully across the so-called dark lane that is adjacent. We're still in the process of examining potential landing sites and traverse routes, but we think we can drive at least half a kilometer and maybe as much as 1 to 2 kilometers. This shows the science team. The deputy PI is Jasper Halikas. Some of the names on here may be somewhat less familiar to this lunar audience because they are members of APL's heliophysics and space physics group, but they've got great credentials when it comes to instrumentation, magnetometers, charged particle detectors, as well as the science thereof. So we think we have a really good team, a good mix of late, mid, and early career people. Just something about the mission's name. In Latin, the word vertex can mean swirl or whirlpool or vortex. But in English, a vertex is an intersection. So we see our mission as representing the crossroads of geoscience and the particles and fields domain of space physics. So we've got an interdisciplinary mission, and this intersection is our theme. Just to conclude, Lunar Vertex is a PRISM mission to the unique environment of a lunar magnetic anomaly. And we're going to be addressing key decadal and scientific context for exploration of the moon questions in major subdisciplines of planetary science. So I'll stop there. Thanks.
Awesome. Thank you very much, David.